Sumedh Soman is a student of Professor Janani. So Sumedh is doing his master's in the University of Colorado Boulder, and he will. The next session is by Sumedh, and it is on turbulence modeling. So Sumedh, you can start your session.
Good afternoon to everybody. Today I'm going to demonstrate the procedure to compile a custom turbulence model on OpenFOAM version 7 using Ubuntu 18.04. This session is based on the work I did under Professor Janani ma'am's guidance during my undergraduate studies as part of the FOSSI semester-long internship. Due to OpenFOAM being open source and free of cost, it is possible to study the source code in detail and implement custom versions of solvers, turbulence models, etc. In case of RAM's turbulence models, different turbulence models are suited to different types of flows. For example, K epsilon is suited to a certain type of flow, K omega is suited to a certain type of flow. In some special cases, none of the existing turbulence models suit the flow case, in which case you have to modify one of the existing turbulence models to actually fit that particular flow case. Of course, it's impossible to implement all such modifications and corrections into one single software. Hence, it is beneficial to know the process to compile a custom turbulence model. Uh, Today, I'll be showing the process to compile the K epsilon model. We will not be making any changes to the source code of the turbulence model itself in this demo, but I will point out at which stage of the process one can carry out modifications to the code. There are some limitations and restrictions. This procedure was developed for OpenFOAM version 1906 and not version 7, which is what is being used. But the file structures in both cases are compatible. Hence, we can go ahead and use this process for OpenFOAM version 7 as well. Due to the uh, pre-compiled version, since we are using a pre-compiled version of OpenFOAM, any change in the version of Ubuntu or any of the dependent libraries may cause the process to fail. So in this case, I will be using Ubuntu version 18.04. We have tried this process with version 20.04, but it did not execute successfully every time. Uh, Workshop participants who are using version 20.04 or above are free to try the process, but there is a possibility that it may fail. And also the code dependency for each turbulence model is different. So this process is only restricted to the K epsilon model. In case one wants to compile a different version, a different turbulence model, the process will be different. Okay, so let us start with the process. I'll switch back to the slide view. First of all, we need to navigate to the working directory of OpenFOAM and copy the source file for the K epsilon model. To that end, we need to copy paste these two lines in the terminal. Now we have copied the turbulence model files into this directory, which I'm showing here. Now the next stage is to actually change the name of the turbulence model, because obviously we cannot have two turbulence models with the same name. So let us enter this new directory that we have created. Now we will rename this turbulence model as my K epsilon. So now the folder name has been changed. It is now my K epsilon, but the file names inside this folder is still K epsilon. So we will need to rename the files inside as well. There are two files inside this folder. There is a header file and there is the actual source code file. I will show the same. So in this my K epsilon folder, we have k epsilon.c, which is the actual source code file, and k epsilon.h, which is the header file. We need to rename both of these into my K epsilon so that it corresponds to the folder name. Ultimately, that is what the name of our turbulence model is going to be.
Hello, one small doubt. Could you tell
Yes.
me what is this P and H file?
The C file is the source code file, which actually has the source code for the turbulence model, and H is the header file. So there are multiple code dependencies. You have to have the mesh data, you have to have the solver data. So all those declarations are contained in the header file. Also, there are several member functions in the source code file for k epsilon, and each of those member functions is declared in the header file. It is more of a coding thing rather than anything physical. It doesn't have a physical connotation per se. It is all coding structure.
Okay, thank
So
you.
I'll rename this file k epsilon.c to my k epsilon.c. Similarly, I will also rename the k epsilon.h file to my k epsilon.h. Now, if we check, we will see that the files have been renamed. However, there is still one thing that is left. The k epsilon, we have renamed the source code files, but the class declaration inside that file is still k epsilon. We will need to change that to my k epsilon as well, because that is the name of our new turbulence model. So for that, we will have to insert this command, where all instances of k epsilon in the .c and the .h file will be replaced by my k epsilon. This is the uh, usage of this command. So let us go and insert it here. Now, if we will open the any of either the header file or the source code file, we will see that there is all the class instances are called my k epsilon and not just k epsilon. As you can see, all instances of k epsilon have been replaced by my k epsilon. Now, at this point, if there are any modifications that one needs to carry out in the source code, it is possible to do that. So, for example, if somebody wants to change the model constants or add some new functions, this can be done over here. This is the part where you can actually modify the turbulence model. Okay, now once we have created the turbulence model of our choice, we need to actually link it to the OpenFOAM installation and compile it. To that end, first of all, we need to copy a file called turbulent transport models.c. Now, what this file is that it contains a list of the turbulence models which are to be compiled by the compiler. It is a file of macros. So let us go ahead and copy this file into our new directory.
I have one small doubt.
Yes,
Overall, what I understood that you have written your own code and you are trying to compile this code with the OpenFOAM environment, right?
yes.
Okay, thank you.
So we have copied the required files into our new directory. So let us go into that directory and rename turbulent transport models.c. So turbulent transport models.c will tell the compiler which instances of turbulence models are to be compiled in the main install directory. We will rename this file to my turbulent transport models, and it will tell the compiler which instances of turbulence models are to be compiled in our new directory. So basically, in this new directory that we have created, we can have n number of different turbulence models. I'll just simply copy this file and rename it. So turbulent transport models.c will become my turbulent transport models.c. Okay, now here what we need to do is open this my turbulent transport models.c file, and we only need to tell the compiler to compile my k epsilon.c. Hence, we will delete all the other lines in this file and just keep these two lines in the file. Okay, so at the end of this step, this is all my turbulent transport models.c should contain. Okay, let's go one step back into the incompressible directory. Now we need to actually link the new turbulence model to the central OpenFOAM install. So I will I'll go to Explorer. So we see this make file here. In that we have two files. Sorry, in the make folder we have two files, files and options. Now these are the files which actually help link the turbulence model to the central OpenFOAM install. So let us open files. So once you open files, you will see all these lines here. We need to replace these lines by the given lines that I have here. So the files so the files file should contain only these two lines. So we will copy these two lines and insert it into our files file here. At this point, you have to be very careful with the spacing and indent because with these sort of files, it's very critical for the compiler to understand. Let us open options. Now we need to add three additional lines here. So three lines here at the end of exe underscore inc and lib dot underscore libs will link the new turbulence models to our existing OpenFOAM installation. Again, at this point, you have to be very careful about the spacing, indent, and the presence of this backslash here. It has to be exactly the same way. So at the end of this step, files should look like this and options should look like this. Now there are very few steps remaining in this process. So first of all, we need to give the compiler a directory, an ln include directory where it can actually store the files related to compilation. So for that, we will copy this line and insert it in the terminal. Now it is simply a matter of typing wmake and the model will compile. Depending on the system you have, it may take a little longer. Okay, so you can see that there is no warning or error message, and that means that the model compilation has been successful. To test whether our model works or not, let's do a trial run.
What wmake ln include does?
So wmake ln include specifies an ln include directory for the compiler. So the compiler on compilation generates some files and it needs to know the location to store those files. So we are going to be storing those here in incompressible. Uh, if I type explorer.exe, you will see that there is this ln include directory. Here's where all the files generated during compilation are stored.
Okay, okay.
Wmake is just the end command to compile the model. Okay, so to test whether our model works or not, let's go back to the main user directory. What I have done is I have copied the PITS daily OpenFOAM tutorial example into this directory in the run directory. Now, to use this new turbulence model, we need to make two changes. First of all, we need to go to constant and we need to change the name of the turbulence model that is specified in turbulence properties. So I have changed the name of the RAS model to be used. It is, since our turbulence model is named my K epsilon, that is what we will write here. This is the first change that we have to do. The second change, we have to go to control dict. And we have created now a new library of incompressible turbulence models, and that is now called my incompressible turbulence models, since our turbulent transport models file has been renamed as my turbulence transport models. So this last line needs to be included at the very end of control dict. These are the only two changes that we need to actually use our new turbulence model. Note that we haven't made any changes to the source code of the turbulence model itself, so the results will be exactly identical as those with a standard K epsilon turbulence model.
What exactly this line means?
So basically we are invoking this new library that we have created. We have created a new library called my incompressible turbulence models. So in order to use this new turbulence model, we have to invoke that library first. It's sort of analogous to writing hashtag include some library when we are writing a C++ code. Does that answer your question? Okay, so let us go ahead and run this simulation.
It is not 100% compiled.
If you will, actually the thing is OpenFOAM is written in C++. So the entirety of OpenFOAM is compiled using a GCC compiler. WMake is a compiler which is built on top of GCC specifically for OpenFOAM. So there is nothing in this procedure which is outside of OpenFOAM per se. Okay, so let's type simple form. Now the simulation is running, but I want to point out one thing here. If you will see, the name of the selected turbulence model here will be my K epsilon and not K epsilon. And if you see this message here, that means that the model is being used in the simulation, and the simulation has also finished successfully. Let us use Parafoam and check the post-processing results. Let us check the velocity field. You can see it is exactly identical to what one would have if we were using the K epsilon model, because obviously we haven't made any changes to the source code of the K epsilon model. So basically this is the process to compile a custom turbulence model in OpenFOAM. Uh, if you're using a different version of OpenFOAM, for example, version 8 or version 9, this process will be different because the file structures for those versions of OpenFOAM are different. This link here can give you some insight as to the process to compile a custom turbulence model for those versions. Thank you.
So thanks, Sumit. So does any one of you have any questions for Sumit? Of course, this link will be shared with you, and I think you can try and replicate it and try and make changes. But would you happen to have any questions?
So if we want to change something in the code, because we haven't changed anything,
Okay.
just rename it and
Right.
change. Can you show some changes
Right.
and then compile?
Okay, it's very simple to do that. So we've been through the entire process. What I'll
Actually,
do
my
is,
concern is dependency. If some dependencies comes in between, then how we can resolve it?
so again, that's the pitfall with this method. Since you're using a pre-compiled version of OpenFOAM, we don't know on which system it was compiled, as in what versions of which libraries it had, what operating system version it had. The ideal method would be to actually compile OpenFOAM on your own system. That is a fail-safe, that is a foolproof method, and it will work every time. But compiling OpenFOAM on your system will probably take upwards of 2 days, because of course OpenFOAM has multiple solvers, multiple turbulence models, etc. But in terms of simply changing constants, adding some filter functions, it generally works without issues. So,
let's say I want to change the constant which is the function of temperature. Let's say, for example. So
okay, so one thing
can
that you
can
have to note is we are using incompressible turbulence models here. So it's a barotropic flow, so we won't have any temperature dependent values. I'll do one thing. I'll go back and I'll make some small change in the code and I'll recompile. That way you can see it works even without.
okay. And it would be function of something, some variable, pressure, temperature. Uh, I just want to see that.
Okay, let's see if we can do something. I'll try to see. So the way I used this process was I was trying to modify a trigger function for intermittency generation in a transition turbulence model. So that is a function of multiple different things, including some boundary layer specific parameters, and it worked in that case. So,
Okay.
okay, so I'll come back to my terminal here. Okay, so this is the source code file. I'll do one thing, I'll open it in a different text editor. Okay, so you can see that there are many protected member functions for different things. So that there's one function for correcting your eddy viscosity. There's one
Mhm.
function for your source for turbulence energy, turbulent kinetic energy. There is one source term for the dissipation rate. And then we
Mhm.
have the constructors here, which are declaring certain constants. Now,
Mhm.
with this, what happens is if the constants are coming from a fixed dictionary of constants, the coefficient dictionary, and
Mhm.
that is protected. It can't be accessed. So if I change that, it will not compile. However,
Mhm.
what we can do is I'll try to see if there's something else that I can change. This is the epsilon equation. So this is the part where we are actually writing out the transport equation for the dissipation rate.
Yes.
So this is the finite volume method library inside OpenFOAM. So this carries out all the finite volume operations such as computing the divergence, computing the gradient,
Mhm.
computing the curl if it's there in any place. And FV options is the library which will allow you to add an additional source term or a destruction term inside the equation. You can use FV
Mhm.
options within control dict and add a constant source term into your
Mhm.
turbulence model.
Yes.
These lines, they basically are for relaxation and under relaxation according to the simple algorithm. This is for constraining the values of the turbulent kinetic energy so that it doesn't turbulent kinetic energy doesn't assume, let's say, a negative value or some garbage value. This is the equation for turbulent kinetic energy.
Mhm.
Again, it's basically the same framework. And at the end, we invoke correct mu t, or basically this protected function right here. So we are just updating the value of the eddy viscosity because at the end of the day, K and epsilon, the eddy viscosity is a function of the turbulent kinetic energy and the dissipation rate, or K and epsilon.
Yes.
What, what I'll do is CMU in this case, CMU is 0.09, it's a constant. I'll just multiply it by 2. I'll go back to the wmake directory. I'll put w clean so that we'll clean the previous compile that we did. What I'll also do is I'll change the timestamp of the turbulent transport models.c file that we have. So to that end, I'll first go into the directory, change the timestamp, go back to incompressible, again, we will have to use the we'll have to specify the directory in this case. Note if you try to compile something like, let's say, the k omega SST model, this process won't work because k omega SST in itself is dependent upon k epsilon and k omega, and k omega SST itself is a base class for other turbulence models which are built up upon k omega SST. So you have to be careful in that area. Again, you can see that the turbulence model is compiled. So I'll just go back to the Pitts daily case. Now, there is a high possibility that the simulation may just crash because we have made a
Yes,
change
yes,
factory
yes.
invalidating the model. But let's see. Again, it took 2 iterations more than normal. Let us just
Yeah,
check whether it actually used the turbulence model that we have created here.
yes, yes, yes. Just-
Okay, so it's using my epsilon, which means, of course, it's our turbulence model. Let's check with the post processing.
Results may be non-physical because
Yes,
you have
it's it
changed. Yeah.
it will be non-physical because obviously the relation
Hmm.
between the eddy viscosity and the
Hmm.
turbulent kinetic energy is wrong in this case. So it obviously looks a little different,
Yes.
right? So you can make similar changes. You can add a separate function and then invoke it within the class where you're actually solving your k and epsilon equations. There are many possibilities. You can check
Okay.
out this reference that I have mentioned here. Uh, they can definitely be of help.
Thank you.
You're welcome.
I have one question. The process that you showed here, is this a general one? Like if at all you want to make any change, for
Right.
example,
So, as I mentioned, this will work if you have Ubuntu version 18.04 and OpenFOAM version 7. We've tried this process on Ubuntu 20.04 OpenFOAM version 7. It worked most of the times, but some trials in it was just inexplicably it didn't work. So uh, I wouldn't say that it will work every time. It may not work. That's this basically this entire issue is a issue with the because we are using a pre-compiled version of OpenFOAM. The process was designed such that you will be using a compiled version, compiled at source version of OpenFOAM. So you will compile each and every solver and turbulence model in OpenFOAM on your system, as opposed to just simply downloading a pre-compiled version. Uh, but that option of compiling at source is only possible if you have very uh, you have high performance computing setups because it takes well over 2 to 3 days at a stretch. But for the OpenFOAM version that I have shown and the Ubuntu version I've shown, it should work fine.
no, what I meant was, suppose like if I want to, the tutorials, the demos we had so far, we had
Mhm.
used the turbulence
Yes, you can use
intensity,
that
like,
this turbulence model that we have created. You can use it in any simulation you want. Just that you have to make the 2 changes that I have described. Changing the name of the turbulence model and writing that last line, invoking the incompressible turbulence model library.
yeah, I understood that, but my question was not regarding this. I was asking a general question. Suppose if instead of like tell we are in the demos, we not this demo, like in the previous in the morning,
Mhm.
there were some demos where we had this turbulence intensity. We were like giving some percentage of the velocity right at the inlet.
Mhm.
And
Mhm.
if instead of that, if I want to give some realistic velocity profile at the inlet, uh, is this the same procedure or something else?
No, no, it will be different. It will be different.
So let
Okay.
me rephrase Abin's question, I think. If I were to want to change anything in the main solver, as opposed to if I want to add an equation, or I want to change an existing solver with, add another term in the equation. Is the procedure overall, which you said, of course, I'll take into account that, turbulence files you've accessed because you're modifying the turbulence. But if I
Right.
were to add an equation or add a term to an already existing equation, typically, is this the procedure that you would follow?
Ma'am, generally the overall workflow will be the same, but then the way we link the solver back to the central install, I think that will be different because the dependencies will be different in that case.
Okay, that by dependencies, you mean the library files.
Yes, ma'am. So for the turbulence model, we will just need the mesh tools library and the finite volume options library, but then the solver will also, I think, have some runtime parameter libraries and some other dependencies.
Okay. Now coming back to Abhin's question, so that's solvers. Now, if I want to change certain input parameters, or if I want to change properties of the fluid to be quite variable, this is of course not the procedure, right? You would go
Yes,
and deal with something else.
yes, ma'am. I think, ma'am, what he means is he wants to assign a different velocity to each cell, is what I thought he was trying to say.
What
That
I meant was I want to say implement a different boundary condition.
right. So again, that the dependencies are different for that. So yes, it won't work with this process. The general workflow will be the same. So copying the files to a new directory, making your changes, linking it to the central install, and setting up the compile parameters and compiling. But the way you link it to the central OpenFOAM install and then the way you actually compile will be different.
So Abhin, does it
One more,
yeah, please go
yeah,
ahead.
just wanted to know, like, is there any reference or a link that you shared? Does it contain the information related to this, or is it only specific to the problem that you discussed now?
No, what I have shared, it's mostly specific to the problem I have described here. But I think maybe if you check out the second reference, it may have something that you need, the second reference here.
Okay, okay, yeah, I will look into it.
Yeah, but
Thank you.
please note it's based on version 8 and not version 7. So,
So one question is from my side, sir.
okay.
So if we want to change the thermophysical properties, of course there are some models already defined, like K is the function of T already we can give. But
Mm-hmm.
if something else we want to give in the thermophysical properties,
Mm-hmm.
so can we do that? I mean, can we change that in the solver, and we can do that, or what we should do?
So I think thermophysical models is described in the constant folder, I believe.
Yes.
So there are different thermophysical models in OpenFOAM as far as I know. Again, it's similar to the solver question that was asked. The general process will be the same, but then the specifics will be different. So the way you link your new thermophysical model to the central install, that will be again different. But the general workflow will be the same.
Can you share some references where thermophysical model have been changed in the source code?
I don't know of such, but maybe you can just check this reference if it might have something. I don't know, but you can try.
I have one small question. We are
Yes,
using different FV schemes, right?
yes.
Suppose I want to develop a new scheme that is all not available in OpenFOAM.
Mm-hmm.
So I just want to ask, like, whether it is possible the way you have shown, the same procedure I am supposed to follow, or how
No,
difficult and easy to compile
if you
the.
will, nay, see, the thing is, if you will open one of the finite volume scheme files, it's actually very, very complicated in terms of code dependencies because one code is relying on the other code, which is relying on two other codes, so on and so forth. It's fairly complicated, and I don't have any experience in that regard. But like I said, the general process, copying your scheme to a new directory, making your scheme like writing your scheme up, linking it to the central install, and then using it. those will be the steps. But again, the dependencies are different. Uh, the code will be different. So the specifics will be different. Like I said, this same process won't even work if you're trying to use the K omega SST model. So uh, it the general row is the same, but the specifics are drastically different if you're going to do something like that, I think.
So essentially,
Okay,
what
thank you.
Sumedh is trying to say to all of you is, so he had to spend several months trying to figure out which are the dependencies for his particular problem, which worked, right? So he used to keep compiling, and there used to be a compilation error. Then he'll add certain dependencies and solve the issue. So maybe you have an overall, so the idea of this particular session was you get an overall view of what things you have to address, but then you go back and to your specific problem, figure out the dependencies, which files are absolutely required for compilation. So that is absolutely essential. Shubham, to your question about input parameters properties, I think transport properties, OpenFOAM gives you a certain number of options to change your input parameters. May it be a tabular column of details or maybe a polynomial.
Polynomial fit, yes.
So there are certain limited options available. There are certain other things like, for example,
Let's say
I understand what you're saying. So there is probably a viscosity model, which
yes.
I might want to change, but the viscosity changes not with temperature, but with something like shear rate, right?
Yeah.
So that means that I am probably getting for every simulation or every time step, I need to get the shear rate, and my viscosity might have to change with that. So that means, again, this process, what Sumedh says applies. We had to figure out what libraries are interlinked to this and then recompile the thing. So it is pretty much same, but again, the dependencies of which libraries are interconnected to your viscosity model and your shear rate model should have to be found out.
Actually, I am working on the phase change problem. So with phase change, suppose something is changing, like density is changing or thermoconductivity is changing. So that phase change, we are representing that merit fraction alpha. So with alpha, if it is changing something, thermophysical property. So how we will incorporate that?
Essentially, this is the process, but you'll have to figure out the dependencies. We have done, you're talking about solidification and melting. So this is a process, but you will have to figure out the dependencies. Basis the solver. Now, the problem here is you'll have to choose the solver, what library files are there in that solver, and deal with it. We were facing a problem where, version 7 had a particular solver. The same solver in version 8 or 9 had different libraries. Okay. So then the model that we had implemented in 7 will not compile in an 8 or a 9, even if you're using the same solver. Okay. So that means the library files, all of those dependencies, you'll have to sort out. Okay. Of course, that's something specific to your problem.
Okay. Thank you,
ma'am. One resource that he can use is the Doxygen documentation files for OpenFOAM are available online. So they have these kind of tree diagrams where they show the dependencies in a flowchart kind of way. Maybe he can use those and see what dependencies are there and what he needs to actually work on.
Okay, can you just type that in the chat box, the Doxygen link, if you might, so that people can access it?
Yes, ma'am. I'll just find that link and I'll share it here.
Okay. Payal, yes.
So it's 3:40 and we can take a 10 minutes tea break. So 3:50 we come back and we will have the session on GUI for OpenFOAM block mesh by Rajdeep Adat.